Okay, so first, the linked list is going to be generic as well. So it's going to be t extends comparable with the t parameter. And basically, this class is going to implement the list interface. Okay, of course, with the t parameter. So I'm going to override these methods. Basically, this is what we are going to implement in this video. Of course, we are going to store a reference to the node. It's going to be the root node. And this is what we have been discussing in the theoretical section, that for the linked list, we are able to access the root node only. And we are able to make all the operations via the root node. So with the help of the root node. Okay. And for example, I'm going to track the size of the list. Size of list. Okay, it's going to be 0 at the beginning. So as far as the insert is concerned, we are going to first increment the size of the list. Okay, then if the root is equal to a null, then we know for certain that this is the first item we would like to insert. So we are going to instantiate it as a new node. And of course, we have to implement, I'm going to get rid of this. And of course, we have to insert this data. Okay. And else, we know for certain that because we have already instantiated the root node is not going to be 0. So we are going to insert data, for example, at the beginning. And we just have to specify the data itself. We can insert data at the beginning and we can insert data at the end. Of course, if we are considering linked list, we usually implement inserting data at the beginning because this is why linked list data structures came to be. It's very efficient to insert items at the beginning. So I'm going to implement it. And basically here we just have to update the references. So I'm going to create a next node with t. It's going to be the new node. It is equal to a new node. And of course, we have to specify the data. So basically, we create a new node with the given data we would like to insert. And then the new node, we set the next node to be equal to the root node. Okay, then this .root node is equal to the new node because we would like to insert a new node at the beginning, right in front of the root node. So we create a new node, we set the next node to pointing to the root node, and basically we update that the root is going to be the new node. We just update the references and update the pointers. Okay, what if we would like to insert at the end? I'm going to implement it, although we are not going to use it. So public void insert data at the end. Of course, we have to specify the data we would like to insert. And by the way, just to be sure that it's clear, it has ordo one-time complexity, and inserting at the end will have the running time ordo n, so linear. Okay, so we have to specify the data, and I forget to specify the node. We have to specify a node, okay. And basically we have to check whether the get next node is equal to a null or not. And if this node, get next node, is not equal to null, what does it mean? That we are not at the end of our linked list. Then we are going to call this insert data at the end recursively with the data, but we are going to specify the next node. So this is how we are going to hop from node to node in order to get to the end of the list. And else basically we are just going to create a new node. So new node, I'm going to specify the data, and we just set on the node that set next node is equal to the new node. Okay, So basically it's going to have linear time complexity. Why? Because first we have to get to the end of the list, and this is why it's going to have ortho and linear time complexity. This operation is very fast. We just create the new node and we update the references as we do it here. But basically getting at the end of the list takes linear time complexity. Okay, so what about the remove method? I'm going to implement the remove method here. If we have to check that this.root node is equal to a null, then of course we know that there is no item at the linked list, so we are going to return. And anyways, we keep decrementing the size of the list, so size of list minus minus, and we check whether we would like to get rid of the root node. So if the root node dot get data dot compare to data is equal to 0, what does it mean? That the data of the root node is equal to the data, so the root node is the one we would like to get rid of, and basically we would like to use this compare to method. If this t wouldn't extend the comparable interface here and in the node class, then we wouldn't be able to use this compare to method in the linked list implementation. And of course we would like to check whether they are equal or not, so that's why we need this t extends comparable. Okay, so if we know that this is the root node we would like to get rid of, then basically we just have to update the references. So the this.root is equal to this.root.get next node. And else I'm just going to call a remove method with the data, with the root node, and with the root node dot get next node. So we have to track the current node and the next node, and of course the data. So I'm going to create this method. I'm going to rename it. This is the previous node, and this is the actual node. This is how we implement it. Okay, at the beginning we insert the root node and the root.getNext node, but in this method we are going to use this root as the previous node and the next node as the actual node, because we keep considering the next and the next items in the linked list. And basically we have to search for the node we would like to get rid of. So while the actual node is not equal to null, I'm just going to check whether if the actual node dot get data dot compare to is equal to the data we would like to remove. So I'm going to rename it to data to remove, because this is the data we are looking for, because we would like to get rid of this data. So if this is equal to 0, we know that we have found the item in the linked list we would like to get rid of. So we just have to update the references. So the previous node dot set next node is equal to the actual node dot get next node. This is what we have been discussing in the theoretical section, and we have to set the actual node to be equal to null in order to avoid obsolete references, because the garbage collector wouldn't be able to collect this reference if it wouldn't pointing to a null. So that's why we set it to null, and basically we return. We don't like to iterate through all the other nodes in the linked list. And otherwise we are going to set the previous node to be equal to the actual node, and the actual node is equal to the actual node dot get next node. So basically we keep hopping from node to node in the linked list, and we keep posing the question that is it the node we would like to get rid of? If yes, then we just update the pointers and make sure that there won't be any obsolete references, and we return, or else we consider the next node in the linked list. Okay, what about the size? We have to override this size method. Basically we just have to return this dot size of list. What about the traverse list? It's going to be, I'm going to implement it in an iterative manner. We can implement it in a recursive manner, but I'm going to use iteration. So first we have to check whether the this.root node is equal to null, which means that our linked list is empty. I'm just going to return. And anyways, I'm going to have actual node. It's going to point to the root node at the beginning. And while this actual node is not equal to null, this is why it's very, very important to track the nulls, because we know that the last item, the last node in the linked list is pointing to a null value. So while the actual is not null, first of all, I'm going to system out println the actual node plus some spacing. I'm going to get rid of the ln in order to prevent making new lines on every iteration. And then of course we have to update the actual node. Actual node is equal to the actual node.getNextNode. Okay, so basically because we have override the toString method in the node, that's why the system out println is going to call the data.toString. So we are going to print out the data in the linked list. So this is how we implement these methods. So we have the traverse list with the help of iteration. We can get the size of the list. We are able to remove and we are able to insert items. We are able to insert items at the beginning and at the end. Of course, we usually use inserting items at the beginning because this is why linked list came to be. In the next video, we are going to test our application. Thanks for watching.